This tutorial extends our study of linear functions. Hopefully from what we did in class today, you got some familiarity with what our book calls intercept form, y equals a plus bx. It's worth noting that most other textbooks call that slope-intercept form. Every linear function can be written in this form, and x and y are going to remain variables when we write our equations. A and b are going to be numbers. And in fact, we can be more specific. We could say that a represents the starting value. That's sort of our sequence way of thinking about it. Or it's our y-intercept. That's a graphical way of thinking about it. It's the point where the line crosses the y-axis. And b, to think about sequences, b is the common difference. It's for each successive term, how much do you add or perhaps subtract. Quite often in real-world examples, it's useful to think of that number as the rate of change. And then graphically, it's the slope or the steepness of the line. So here's a bunch of examples. Y equals 2 plus 5x. I know that's a linear function because it's in a plus bx form. And in fact, I know that the starting number, when x is 0, it's 2. That's what this 2 right here tells me. I also know that as I go up 1 for x, that the y value is going to go up by 5. So it won't be 2 anymore, it'll be 2 plus 5, or 7. And if x goes up 1 more, from 0 to 1 now to 2, the y value is going to go up 5 more, so 7 plus 5 is 12. You could also get those numbers by plugging 2 in for x. So 5 times 2 is 10, plus 2 is 12. Similarly, this also represents a linear function, and if you thought of it as a sequence, the 0 term would be 17. If you plug in 0 for x, you get 17 minus 4 times 0, or 17 minus 0, which is 17. And then as x increases, in this example, y is going to decrease because it's minus 4x. So 17 minus 4 is 13. And then if you increased x 1 more, y would go down by another 4. 13 minus 4 is 9. And one more example. This sort of looks like the calorie burning examples that we did in class. So at the beginning, times 0, you've already burned 225 calories. And then with each passing hour, I guess, or minute, I don't know how we're measuring it, you burn another 120. So after one additional unit of time, we would add 120 to the 225, and we'd get 345. Okay, so that's 3 examples of linear functions written in intercept form. One way to think about linear functions is with inputs, or x values, and outputs, y values. So what I have here is a table that represents the number of weeks and in the input, and the output is the amount of money that somebody has. So in this example, you can see that week 0, so at the start, this person has $125. After 1 week, the person has increased their amount of money to $175, and then 2 weeks, $225, and so on. So if you look at this, you might be able to discern the pattern fairly quickly, and then the challenge is to then write it as an equation. So somewhere here there it is. The equation is y equals 125 plus 50x. Start at 125, and then each time you go up 1 week, you increase by $50. 125 plus 50 is 175, and so on. Occasionally, you might be confronted with a table whose input values don't increase one at a time. So this is a linear function that models distance from some location that you're driving to. So at the start, you're 540 miles away. After 4 hours of driving, you're 340 miles away. So you're getting closer. But instead of giving you each and every hour, I went in blocks of 4. So if I asked you to write the equation that goes with this, you might be tempted to write 540 minus 100x, because it's starting at 540, and as you go down the chart, it keeps decreasing by 100. But if you think about it, you'll realize that that is not quite right, because, I better cross it out, if you plugged in, say, 4 for x, well, 100 times 4 is 400. 540 minus 400 is 140. So that doesn't work. What's happening here is we can't just take this difference of 100 and assume that's the rate of change, because that took 4 hours to happen. So here's what we need to do. We need to think about it this way. Well, let's look at these two rows on the chart. Okay? So what happened to the miles? Well, they went from 340 to 240. So 240 minus 340, that was the change in the miles. And then, but that took from 4 hours to 8 hours, so 8 minus 4. Okay, so here's what I'm saying. The distance went down 100 miles, but it did that over the course of 8 minus 4, or 4 hours. You divide that out, and what you discover is the rate of change here is negative 25. Each hour, the miles decrease by 25. So for every 4 hours, it makes sense that they decrease 100. So the correct equation to model this chart is y equals 540. That's where we're starting. And then we're decreasing at a rate of 25 miles with each hour. Okay. For your homework, I have 2 charts that I want you to complete. Assume that they're linear relationships. Figure out what the pattern is as you go down the chart from 7.2 to 8.5. And use that pattern to fill in these missing spaces. And then give me the equation in slope-intercept form, y equals a plus bx. Notice that in this first table, I did increase my x values one at a time. So that one requires slightly fewer steps than this one. Because over here, notice my x values went up 5 at a time. So you're going to have to think a little bit on that one, how to find the rate of change. Also, please note on this one, it will involve decimals. Even though only whole numbers show up on the chart that you see, you'll end up with decimals in your equation. Okay, see you tomorrow.